Hi students, Mrs. Bowles here. Planning today to talk a little bit about thermochemistry, specifically matter and energy. So let's get right into it. You've been looking into energy and I've been having you do some thinking about that. Just for a formal definition, it's the capacity to do some kind of work. So you've heard a lot about different forms of energy in your previous knowledge of science and physical science. Energy is always involved when matter is changing. And I had you look at things such as why different metals feel cooler than the wood themselves, and whether or not the ice would melt on top of those. And when you saw that, you may have begun to notice that not all matter is the same when it has to do with energy and how it absorbs or allows energy to go through it. To get a little more detail here, sometimes systems take in energy from their surroundings, and we call that endothermic. The prefix endo means in, and thermic means heat. So endothermic, these are reactions that take in heat, and reactions that give off heat are called exothermic, or allowing heat to leave or exit the reaction. This particular picture with the cold pack represents an endothermic reaction or system, and these kinds of things often feel cold. Now, the reason why they feel cold is because the surroundings around the reaction, the energy has been entering into the reaction, endothermic, and therefore the surroundings will appear cold. It's a little bit strange and almost seems contradictory in your brain, but this is true of endothermic. Exothermic, on the other hand, these are reactions that typically give off heat, give off energy, so they will typically feel warm. You might see light or heat coming from them. Now, what we're really talking about in these heat changes is we're talking about changes in something called enthalpy. Now, enthalpy is related to energy quite closely. It's the total energy content of a sample, has to do with the particles, the way that they're behaving, and it has the letter H in chemistry. So when we talk about changes in this enthalpy, we talk about something called delta or triangle H. So when a reaction is exothermic and it gives off heat to its surroundings and it's getting hot to the surroundings, that's called exothermic. So it has a negative delta H. And as you might expect, endothermic reactions, because they're sucking in heat from their environment, they tend to feel cold on the outside. These are positive in their delta H. So just a few reviews on that with this graphic. Releasing heat makes it exothermic. Remember, heat exits. So exothermic, heat goes out. Endothermic, heat goes in. Enter, endo, exit, exo. Okay, so take a look at here. You might notice that when the reactants become products, they give off energy or heat. That would be represented by exothermic, heat exiting. Now, if you were seeing it in a graphical form, this is actually called a potential energy diagram or an energy diagram. Notice on the y-axis, it has energy listed here, and as you're going to learn, the units for energy are things like joules or kilojoules and also calories. So they've listed that. Here they're showing you the forward reaction, which means we're starting here, and we're going up over this big hill, and then we're ending here. So this reaction, in order for it to proceed, starts at low energy, in fact it's negative kilojoules, and goes to higher energy. Think for a moment before you go on. Would that be endo or exothermic? The answer is endothermic. I hope you got that one right. The reason why is because heat is going into the system from the surroundings. How do you know that? It starts with low energy at the reactants here. It goes over a large hill and it ends with higher energy. The only reason why it can end with higher energy is because energy has gone into the system, allowed the particles to speed up, and now they have a greater energy content or enthalpy. What about this one? Take a look at this one. Similarly, energy is graphed on the y-axis, and on the x-axis is the reaction progress. So we're starting our system, our reaction is starting here at -3 kilojoules of energy, going over the hill, going down, and now it's ending. The reaction's energy is ending at -37 kilojoules. So take a moment before you go on. What do you think? Exothermic or endothermic? If you guessed exothermic and you notice that the reactants are higher energy than the products, therefore heat must have been exiting the system. Energy is always either coming in or going out or staying the same. So let's see, let's test your endo and exothermic brain. Let's see how you're getting along with these. So here I have some examples I want you to think about. And if you're needing more time to think, stop my video in between and take a look. So what do you think? This would normally be a partner check-in in class. So here's your first one, a liquid changing to a solid. Think about that one for a minute before you go on. Second one, a solid changing to a liquid. Now obviously whatever you choose for A, B cannot be the same because they are opposite processes. Keep that in mind. Here's C, a gas changing to a liquid. Think about that one. And D, a liquid changing to a gas. So you have your answers locked in. Which is endo? Which is exo? And here are your answers. A and C are both exothermic, while B and D are both endothermic. How do you think about this? Remember, endothermic heat is going in to the system. That means the particles are going to speed up because they're taking in heat. So that means on B and D, notice it goes from a low energy state, very little movement of particles, to one that's moving fast. So when you think about what is happening to the energy in the various components and how did it change? Solids must speed up to become liquids. That's why it's endothermic. Liquids must speed up to become gases. So if they're increasing in their speed, they're increasing in their energy, that's endothermic. If they're decreasing in their speed and their energy, that means they're releasing to the environment. That would be exothermic. So exothermic slows down, endothermic speeds up and gets more energy. This is actually a law, my friends. There's a law of energy transfer. I don't know if you know it from your previous research, but it's called the law of conservation of energy. It's just like the law of conservation of matter or mass. You cannot create or destroy energy. You merely change it or transform it in chemical reactions. So when you think about some of these systems, like an ice cream cone being digested in your body to give you energy to ride a bike, those are energy transformations, abiding by the law of conservation of heat energy. And that's about all I have for you on this one. We're going to come back and talk about heat and temperature soon.